This video, we're going to look at some further properties of integrals, but I must point out that students of the past used to spend a lot of time solving problems of integrals. I'm not going to do that because that would occupy an entire course in and of itself. And today, it's possible to use various types of programs that are out there. For example, Wolfram Alpha, Photomath, or CY Math are just a couple of examples of various kinds of programs that are available on the internet or on your telephone that you can use to solve problems of integration. So let's look at some of the properties. If A, B, and C are points in two space such that A is less than B, which is less than C, then we have these properties. One, the integral from A to C of f of x dx is equal to the integral from A to B plus the integral from B to C. The second property is that the integral between 2 points A and A is effectively equal to 0. The third property is that the integral from C to A of f of x is the negative of the integral from A to C of f of x. So in other words, reversing directions of integration reverses the sign. The fourth property, if function f of x is negatively valued on the closed interval A to C, then the integral from A to C of f of x dx is less than 0, where the absolute value of the integral from A to C of f of x dx is the area of the region between the curve fx and the x-axis between points A and C. As an example of this particular property, consider f of x equal to minus 2x minus 1. We're going to take the integral from 0 to 2 here, and we find that when we do that, we get minus x squared minus x evaluated at 0 and 2. And that gives us the result minus 6. But remember, the area is the absolute value, so then it's 6. We can't have a negative area, of course, in economics because we're always dealing with the positive plane. We're always dealing with positive variables. In economics, the area of most interest are the consumer surplus and producer surplus, which I often refer to as quasi-rent. Now, we write demand as the price demand. It is a function of Q. So then consumer surplus in the diagram here, the consumer surplus is given by the derivative or the integral from 0 to Q, 0. So from 0 to Q0 of this function d of q of your marginal willingness to pay, and then this becomes the area under the curve, but we need to, because it's this area is included in there, we need to then subtract from that the amount P0, Q0. Otherwise we get the wrong answer here. The next thing is that the producer surplus is the area above the supply or the marginal cost function. So if it's a marginal, remember, then it's a total. For example, here we had marginal willingness to pay, and the consumer surplus is the total willingness to pay as the area under the curve. But of course, we had to subtract that cost of purchasing the Q amount, Q0 amount. So here, the producer surplus is given by the area above the supply curve and below the price 0. So the way we calculate it is we take this entire square or this entire rectangle, and that's given by this amount here, which is our total revenue, and we subtract from that the area below. So this area here is the area underneath the supply curve, and that equals our total variable cost, and we subtract that from the total revenue to get the producer surplus or the quasi-rent. Now consider a change in producer surplus because prices increased from P0 to P1. Now that's a bit more complicated to figure out, But here you're interested in the shaded area that is shown. And to get that, we take the entire total revenue under the new price and new quantity, subtract from it the old revenue. So in other words, we're looking at this entire area here that I'm dotting in red, and we're then subtracting from that dotted area, which is given by these two expressions. We have to subtract from that the area from Q0 to Q1, the area under the supply curve. Here's another instance of just calculating the producer surplus, where we have a point here where it intersects, the supply curve intersects the horizontal axis. So we don't want to include this area that I'm dotting in red, but rather we want to look at the total revenue, P0, Q0, and subtract from that only this red area here that I'm shading here, and ignore that area underneath the curve beyond or before QM. So then what we're interested in is total revenue minus that red shaded area here, which is given by Q, the integral from QM to Q0. Now we also have improper integrals, and there are two types. Functions where the lower limit approaches minus infinity, or where the upper limit approaches plus infinity, or both. The other one is discontinuous functions. If a limit exists, then the integral from a to plus infinity of f of x dx is equal to the limit as c approaches infinity of the integral between a and c of the function f of x. The second case is a negative infinity to c of f of x, and here we define a to approach negative infinity, and we have that the integral from a to c of f of x dx, where a approaches the negative infinity. And then we have the case of going from negative infinity to positive infinity. You can think of a Gaussian function, so your standard normal distribution looks like that. And now what we do is we break it into an interval from a to 0, from the negative infinity to the 0, and we have a approaching negative infinity of the function f of x, and then we have the second component, which is the limit as c approaches infinity, and here we take the integral from 0 to c. Okay, we want to look at an example from Hoy et al., pages 615 and 616, where we want to find the consumer surplus. And we're going to do it in two ways, and they should give you the same answer. So the question here is, we have an ordinary demand function, which is given by Q equals 50 times P to the minus 2. And we want to find the consumer surplus if P equals 10. So let's look at it first from the function P as a function of Q. So we rewrite this particular equation as P equals 50 over Q, all to the power 1/2. So the square root of 50 over Q. So in order to integrate that, we want to integrate between 0 and 1/2, and we want to look at this shaded area. But when we integrate from 0 to 1/2, we capture not only this shaded area, but also this area here, 10 times 1/2, or 5, which is equal to the purchase cost. So we have to subtract that from the integral that we get, this integrated area here. And once we do that, we should come up with the correct answer, which will turn out to be a consumer surplus of 5. So let's look first at this little part here. When we integrate that, what do we get? Well, we can take the square root of 50 out, and then we integrate Q to the minus 1/2. Doing that gives us 2 square root 50 Q to the 1/2. So now, substituting that in, we have no constant of integration because we really don't need it, because we're integrating from k, or from 0 to 1/2. And we let k approach 0 because everything at 0 is kind of funny. So what we do is we integrate this, and we come up with a limit as k approaches 0 of 2 times 50 square root of 50, times q to the 1/2. So we have k 1/2 to the power 1/2 minus k to the power 1/2. But k to the power 1/2 as k approaches 0 is effectively 0. So we get 2 times the root of 50 times 1/2 square root of 1/2. So think about it. So we get 2 times 5 because we take 25 out of here and we have a square root 2 left, but we're dividing by a square root 2. So it's, in essence, we've got 2 times 5, which is 10, minus 10 to the 1, 10 times 1/2, which is 5, which gives us 5. Now let's look at it the other way. So here we have our original ordinary demand function, Q equals 50 over P squared, which when we draw it in the coordinate system, we have P on the horizontal axis, Q on the vertical axis. And now what we're interested in is this area here from 10 to infinity. So now what we do is we again take this and we're going to integrate from 10 to infinity, and we're going to substitute for infinity. We're going to put this k here again and let k approach infinity. So now if we look first at this, we find that if we integrate this, we get 50 times the integral of 1 over p squared dp, which is equal to minus 50 1 over p. Remember, we got p to the minus 2, and we're going to add a 1 to that, so we'll get p to the power minus 2 plus 1, which is p to the minus 1, which is 1 over p. We had that negative because it is p to the minus 1, and then this is this constant of integration, which we're going to drop. So we get this integral. The consumer surplus is the integral from 10 to infinity of 50 p to the minus 2 times dp, limit of k approaching infinity. We get 10, the integral from 10 to k times, or the integral of 50 over p squared dp, and that gives us the limit as k approaches infinity of minus 50. There's that minus 50. K to the minus 1, so that's that p is now, we substituted k for p, and we substitute 10 for p. So we're looking at the area from here back down to 10. So we get 10 minus 1, k minus 1, but k is going to infinity, so 1 over infinity goes to 0. So we get minus 50 times minus 1/10, which again is 5. Now, if the limit exists, then the fourth property is that if f of x is continuous on the half open, so it's open on the side A and closed on the side C interval, then the integral from a to c of f of x dx is given by the limit as a small epsilon approaches 0 from the positive direction. So then we have the integral going from a plus epsilon to c, and this epsilon is approaching 0, and it's an integral over the function f of x. If f of x is continuous on the half open interval, but on this case the interval is open on the right hand side on c, then the integral from a to c is of f of x is given by a limit. Again, we postulate this little epsilon, which is then being driven to 0, and in this case we subtract the epsilon from c, and we use that to solve the integrate that function f of x over that interval. Now, if f of x is continuous on the interval, closed interval on the A side, open on the B side, and then from the B side is open to the C side is closed, which means that at point B there's some kind of discontinuity in the function. Then what we do is we integrate from A to C by simply setting up these two integrations from A to B minus epsilon, where epsilon is driven to the limit 0 of f of x plus some delta going to be driven to 0 of b plus delta to c of f of x. Suppose that q is p to the minus 1/2 minus 1. What's the change in consumer surplus if the price falls from p equals 4 to p equals 0? In that case, we calculate the amount, the change in consumer surplus to be 16. But we can look at it a little different later on. Techniques of integration. the substitution rule, f of u is the integral of big F of u is the integral of small f of u, so that the first derivative of the function capital Fu du equals the lowercase fu, and u equals g of x. Then we find that the integral of small f of u multiplied by du dx is equal to big F of u plus c, or the integral of little f as a function of g of x multiplied by the first derivative of g of x with respect to u, of course, times dx is equal to big F u plus c. We already talked about that in the previous lecture, so you should go back to that. The second is integration by parts. Let's let u equals f of x and v equals g of x. Then the integral of v du is equal to uv minus the integral of u dv. Or, in other words, g of x, f prime x, d of x is equal to f of x times g of x minus the integral of f of x times the first derivative of x. Integrals depending on a parameter. F of x, big F of x, is the integral from a to u of x of fz dz, where z is an integration dummy parameter. And that implies that the first derivative of the big function f of x is equal to the partial of big F with respect to u times the partial of u with respect to x, and that's equal to the f of u, the original function that we wanted to integrate, times du dx. And then that antiderivative, if you like, the big F of x is equal to a lower bound, the integral from the lower bound of x to b of fz dz, and that implies that the first derivative of that f of x is equal to the partial of big F with respect to the lower bound multiplied by the partial of the lower bound with respect to x, which gives us small f minus small f of the lower bound times the partial of the lower bound with respect to x. And then we have generalization, Leibniz rule, where you can look at that yourself, but there's a way that you can then find that big F of x function as well. And there's some further generalizations here, so that the big generalization is that you use this particular expression, this one here, to find the integral of the function f of z y of, and that should be a z as well. Oops. So let's look at an example. For the demand function q equals 5p to the minus 1/2 minus 1, what is the consumer surplus change if the price falls from P4 to P0, so it becomes a free good? Notice that in this case I've got P on this axis, Q on the vertical axis. We find that the price goes from 4 to 0, and we're interested in this shaded area that's shown, which is equal to the limit as a approaches 0 of the integral from a to 4 of the function 5p to the minus 1/2 minus 1, which is our demand function, and we work it through. We let this a approach 0, so the limit as a approaches 0 of a to the 1/2 is 0, and the limit as a approaches 0 of a is 0, and we get the result that we get 16 as our change in consumer surplus. Thank you for watching this video. There are many more videos in this 2 to 3 course series. A list of videos, the order in which they should be taken, and links to them are found under Mathematical Economics at the website indicated below.